Today we'll be looking at vertical and horizontal asymptotes. So to begin, let's look at what asymptotes are. Asymptotes are values or lines that a graph approaches but never touches for large values of x. Believe it or not, a function can cross a horizontal or oblique asymptote for small values of x. And also horizontal and vertical asymptotes play an important role in curve sketching. So when we're looking at our asymptotes, you're going to be looking at the limit as x approaches your c from both the positive and negative side. So we're going to use that notation for looking at it as it approaches positive and negative infinity. However, this doesn't actually exist for these asymptotes here. So these limits will help us to form a basis for determining asymptotes to simple rational functions. So first, looking at our vertical asymptotes, these can be found in rational function in the form f of x equals p of x over q of x at x equals c. So let's look at an example to begin here. Our first example is f of x equals x over x squared plus x minus 2. Anytime we're finding our vertical asymptotes, what we need to do first is we need to factor our denominator. The reason we factor our denominator is because then if we set our denominator equal to 0, then it's easy to find what our vertical asymptotes are. So looking at this, we have f of x equals x over x plus 2 times x minus 1, since 2 times negative 1 gives us negative 2, and 2 plus negative 1 gives us positive 1. So therefore, what values of x make the denominator equal to 0, x equals negative 2, and x equals positive 1. And these are what we call our vertical asymptotes. So now in part 2 here, we want to determine the behavior near the asymptotes. So we're going to look at our x values and look at them in regards to our asymptotes. We're going to look at our function f of x equals x over x plus 2 times x minus 1 and look at it where it's positive and negative. And therefore we're then going to look at, well, what is f of x approaching then? So we're first going to look at as x approaches negative 2 from our negative side, as it approaches from the positive side, and then looking at our asymptote of positive 1 from the negative side and from the positive side. Remember, when I say negative side, I'm referring to left side. As I'm saying positive side, I'm referring to the right hand side. So let's take a value for our first one of x equals negative 2.1, since this is on the left hand side of negative 2. So I'm going to get a negative in my numerator here over a negative times a negative. Therefore, this will give me a negative. And we know that our function is approaching negative infinity. Now what about when x is approaching negative 2 from our positive side? Then x would be equal to, say, negative 1.9. So remember, the values don't actually matter what you take. I just take a value that is very close to our asymptotes, just not our asymptote. So x is equal to negative 1.9. So we have negative over a negative times a negative, which gives us a positive. Therefore, our function will be approaching positive infinity. Now looking at our asymptote of 1 on the left-hand side, we're going to take the value of 0.9. So we have a positive in my numerator over a positive times a negative, which will give me a negative. So therefore, I know this is approaching negative infinity. And if we look at on the right-hand side of 1, so say 1.1, we have a positive over a positive times a positive. Therefore, our function would be positive, and therefore our function would be approaching positive infinity. Now, in part 3, we want to sketch the behavior. So when we're sketching this behavior here, what we're going to do first is draw in our asymptotes. So our first asymptote is at x equals negative 2. And our other one is at x equals 1. So x equals 1. And we're going to look at then our behaviors here. So as we're looking at x approaching negative 2 from the left-hand side, our whole function will be approaching negative infinity. As it approaches 2 from the right-hand side, it's going to approach positive infinity. As it approaches left-hand side, as x approaches 1, it is approaching negative infinity and then positive infinity. So that's all I want us to do at this present time when I'm talking about sketching our behavior. But in our next examples, we'll be looking further using our different asymptotes. So the graph of f at x has a vertical asymptote x equals c if one of the following limit statements is true. So if the limit as x approaches c from our negative side of our f at x is equal to positive infinity. So we have our asymptote equal to x equals c if it's equal to positive infinity. So we'd have something looking like this. Then we know that that the limit is true there and that the graph of f at x does have a vertical asymptote. So next, if we're looking at our vertical asymptote again at x equals c, if it's approaching c from our negative side and our whole function is approaching negative infinity. Similarly, looking on the right hand side of our vertical asymptote, looking at it as it approaches positive infinity, and then looking at it as it approaches negative infinity. So this is just stating that the graph of f at x has a vertical asymptote if one of those statements are true. So looking at our horizontal asymptotes now. So horizontal asymptotes are found by analyzing f at x as x approaches positive and negative infinity. So there's 3 different situations. These situations are situations that we covered in advanced functions, but we should definitely be aware and understand them here in calculus. So when our degree of our numerator is less than our degree of our denominator, we know our horizontal asymptote is going to exist at y equals 0. So an example of this is just that f at x is equal to x over 3x squared plus 6. Now, our other example or case here, if our degree of our numerator is greater than our degree of our denominator, if this happens, we have no horizontal asymptote. So an example of this is just that f at x is equal to x squared all over x plus 2. And our last our case here is our degree of the numerator and denominator, so of the highest degrees we're talking about in each case, are equal to one another. It's going to actually be equal to the coefficient of the highest degree in our numerator over the coefficient of the highest degree in our denominator. So an example of this is just that f at x is equal to, say, 2x squared plus 4 all over 3x squared. So we just take our coefficients, so say 2 and 3 of our highest degree to find our horizontal asymptote. So therefore, our horizontal asymptote in this case would exist at y equals 2/3. So just to note here, the vertical asymptote or asymptotes are found by analyzing the function of y values approaching positive and negative infinity. And the horizontal asymptote or asymptotes are found by analyzing the function of x values approaching positive and negative infinity. So we just are giving little examples there as a limit of x approaches positive infinity of 1 over x equals 0, and our limit as x approaches negative infinity of 1 over x is also equal to 0. So one rule of thumb with functions is to try to write them such that the highest degree is a factor. So in our next example, we want to determine the horizontal asymptotes using limits. So this takes us back to our unit 1. Now, when we're talking about our horizontal asymptotes, what you want to do when you're trying to find limits is you're going to divide each thing by the highest degree in the whole function. So looking at a here, f at x equals 3x squared plus 2x all over 4x to the power of 4 plus 3x cubed plus 1. Our highest degree in this case is our x to the power of 4. So we are going to divide each term in our function by x to the power of 4. So we take our function, and like I said, we're going to do exactly that, divide each term by x to the power of 4. Okay, so we can now simplify this, so we get 3 over x squared plus 2 over x cubed all over 4 plus 3 over x plus 1 over x to the power of 4. Now, oops, sorry, this should have been written differently there. Pardon me for that little mistake. Is that we're supposed to be looking at the limit as x approaches infinity. So as x approaches infinity, we're looking at our function here. And what we get then, make sure that my equal signs are in the right place as well. So what we get, and when we put in a value that is getting larger and larger, so you can put in a value of say 100, you can then look at a value of 1,000. What you're going to notice is when you take 3 and divide it by that number, it's going to get smaller and smaller and smaller and smaller, and it's really what it's happening is it's approaching 0 closer and closer. So that's going to happen to each of our terms here except for our term of 4, since 4 doesn't have any x's in their denominator. So we're going to have 0 plus 0 over 4 plus 0 plus 0. 0 divided by 4 is actually just going to be equal to 0. So therefore we have a horizontal asymptote at y equals 0. Now please do note that when we're talking about finding our horizontal asymptotes, you don't need to always do the limit. The limit you only need to do when it tells us find your horizontal asymptotes using the limit. Otherwise, we can look at the 3 cases that we discussed above. Because looking at part A here, the degree of our numerator we see is less than the degree of our denominator, therefore we know that's one of our cases, and therefore a horizontal asymptote would exist at y equals 0. Okay, so in B here we have f at x equals x cubed plus 2x all over 2x squared plus x. Our highest degree here is our x cubed, so you're going to divide everything, so each term by x cubed. So as you take the limit as x approaches infinity, you're going to divide each term by your x cubed, as I have already said. And when we simplify this, we're going to get that the limit as x approaches infinity is equal to 1 plus 2 over x squared all over 2 over x plus 1 over x cubed. So similarly, as in part A, we are going to have 1 plus 2 divided by a larger and larger and larger number is going to be that it's approaching 0. So 1 plus 0 over 0 plus 0. So this would be 1 divided by 0. Now, 1 divided by 0, that does not exist. Okay? You'll get an error by putting it into your calculator if you try. So therefore we have no horizontal asymptote. Again, if this is shown by one of our cases, the degree of the numerator is greater than the degree of the denominator. So we know therefore that we would have no horizontal asymptote. So when discussing horizontal asymptotes, if the limit of x is approaching positive infinity of f at x equals L, or if the limit as x approaches negative infinity of f at x equals L, We say that the line y equals L is a horizontal asymptote of the graph f at x. So, in our next example, we want to determine the asymptotes, describe the behavior near the asymptote, so in that chart that we used in our first example, and provide a sketch for each of the graphs. So that's what we're going to do. We're going to start off by always factoring our function. So we have x minus 2 all over. Two numbers that multiply to negative 6 and add to positive 1 are going to be positive 3 and negative 2. So you see here that these negative 2, x minus 2, are going to cancel out, and we're going to be left with 1 over x plus 3. So therefore, since I canceled out my whole expression here of x minus 2, we therefore know we have a whole at x equals 2. So since we have that whole at x equals 2, we know that when we graph this, there is going to be an open circle. So at x equals 2, and we know that we have a vertical asymptote at x equals negative 3. Now talking about our horizontal asymptote, so you can go ahead and actually do the limit, or you can use the fact of our three cases. So you notice here that the degree of the numerator is less than the degree of the denominator. And when this happens, we know that we have a horizontal asymptote at y equals 0. So now we're going to go ahead and look at our behaviors near our asymptote. So we're going to look at those and our function, and we're going to look at what our function is approaching. So we're going to look at as x approaches negative 3 from the negative side, from the positive side, and we're also going to look at as x approaches negative infinity and positive infinity. So when we're looking at x approaching negative 3 from the negative side, if we were to take a point, say negative 3.1, we're going to get that our numerator is positive and our denominator negative. Therefore, our function would be negative and therefore approaching negative infinity. As x approaches negative 3 from the positive side, we have a positive over positive, therefore giving us a positive, and therefore our whole function would be approaching positive infinity. Now, when x is approaching negative infinity, I want us to just take a very large number. So let's take f of negative 100. So looking at f of negative 100, that's going to be equal to 1 over negative 97, which is less than 0. So therefore we know that it's going to be below our horizontal asymptote. Now when we look at x approaching positive infinity, let's look at the value of 100 for our x, which would then give us 1 over 103, which is going to be greater than 0, and therefore we know it's going to be above our horizontal asymptote. Now before we can go ahead and sketch this, we need to find out a couple other values. So where is our y-intercept? So our y-intercept exists at x equals 0. So f of 0 is actually going to be equal to 1/3. And looking at our whole at x equals 2, f at 2 is going to be equal to 1/5. So now we can use all of these values using your asymptotes, using your behaviors, using your specific points here, and we can go ahead and sketch this. So our first step here is to graph our asymptotes. So we know we have a vertical asymptote at x equals negative 3, so we can draw in our dotted line there. Always make sure that you do label all of your asymptotes. So this would be x equals negative 3. We also know that we have a horizontal asymptote here at x equals 0. Now another thing that we know is that we have specific points, so 0 and 1/3. And we also know that we have our whole at 2 and 1/5. Okay, so now let's look at our behaviors here. So let's look at first when it's approaching -3 from our left hand side. So we know it's going to be approaching negative infinity. Also, when x is approaching negative infinity, we know it's going to be below our horizontal asymptote. So we're going to have our graph look something similar to this. Remember, this is just a sketch, so I don't need specific points except for our main specific points, such as our whole and our y-intercept. Okay, another major point would be your x-intercept if one existed, but there isn't one in this example. So now let's look at, as x approaches -3 from our right hand side, we see that our whole function is approaching positive infinity. And as x approaches positive infinity, we see that it's going to be above our horizontal asymptote. So we can draw in our graph to look like this. And make sure that we label, so f at x is equal to x minus 2 all over x squared plus x minus 6. And there's our sketch. Now in part B, we have f at x equals 3x minus 6 all over x plus 2. So we can go ahead and look at, well, where is my vertical asymptote? So my vertical asymptote, remember, we always look at our denominator. So in this case, our vertical asymptote is going to be at x equals -2, because if I subbed in -2 there, it would make our whole denominator equal to 0. Now what about our horizontal asymptote? Well, what we notice here is that our highest degree of both our numerator and denominator are equal to one another, so you take the coefficients of those highest degrees and you take the numerator, which is 3 over 1. So it's just equal to 3. So therefore, your horizontal asymptote exists at y equals 3. So now we can go ahead and look at our behaviors. Okay, so we're going to look at our f at x, our function, and we're going to look at what is my function approaching then. So as x is approaching -2 from the negative side, from the positive side, and as x is approaching a positive infinity and negative infinity. So as x is approaching -2 from the negative side, so if we were say take the value of -2.1, we're going to get that it's a positive over, not a positive, pardon me. We're going to get that it's a negative over a negative, which gives us a positive. I was just jumping to our answer there, which gives us a positive infinity. Now, as x approaches -2 from the positive side, this is going to give us a negative over a positive, which gives us a negative, and therefore our whole function is going to be approaching negative infinity. Now, as we are looking at x approaching positive infinity, we are going to again just take the value of 100. We're going to get that it's 294 over 102, which is less than 3. The reason we're looking at 3 is because we have a horizontal asymptote at y equals 3. So therefore we know since it's less than 3, it's going to be below our horizontal asymptote. And if we look at as x is approaching negative infinity, we're going to get a value of -306 all over -98, which is actually going to be greater than 3, and therefore we know it is above our horizontal asymptote. A couple other values that we need to make sure that we look at. First is our y-intercept. Remember, x is equal to 0 at our y-intercept, so if we sub in 0 there, what we're going to get is -3. Also, let's look at our y-intercept. So remember, our y-intercept exists when y is equal to 0. So we have 3x minus 6 all over x plus 2. I'd cross multiply here, and therefore I'd have 0 equals 3x minus 6. So then I will bring that 6 over to my left-hand side. So I have 6 equals 3x, divide both sides by 3, and therefore we'll get that x is equal to 2, and we have our point 2, 0. So now I have enough information that we can go ahead and sketch. So our first step here is to graph our vertical and our horizontal asymptotes. So we have a vertical asymptote at -2. Make sure to label, so x equals -2, and we have a horizontal asymptote at +3. So y equals 3. So now we also want to plot our points, okay, so our x and y intercepts. So our y-intercept is at -3, so 0, -3. And our y-intercept is at 2, 0. Sorry, our x-intercept, I don't know if I said y there by accident. Now let's look as x approaches -2 from our negative side, we know our whole function is going to be approaching positive infinity. And as x approaches negative infinity, we know it's going to be above our horizontal asymptote. So we're going to have our graph look something similar to this. Next, as x is approaching -2 from the positive side, so our right-hand side, our whole function will be approaching negative infinity. And as x is approaching positive infinity, we know that it's going to be below our horizontal asymptote. So what we have here, make sure we go through our x and y intercepts. We have our function to look something similar to this. Make sure that we label our function, so f of x equals 3x minus 6 all over x plus 2. And that is our sketch. So example 4, given f of x equals 3x squared plus 4 all over x squared plus x minus 6, determine the equation of all horizontal and vertical asymptotes, the behavior around the asymptotes, and provide a sketch. So again, factor our function. So we have 3x squared plus 4 all over x plus 3 times x minus 2. Okay, next we look at, well, where are my vertical asymptotes? So remember, vertical asymptotes come from your denominator, so we have x equals -3, then x equals +2. Now what about your horizontal asymptotes? So looking here, you see that your highest degree of your numerator is 3x squared, and your highest degree is x squared in your denominator. So again, it would be 3 divided by 1, which is 3, so you have a horizontal asymptote at y equals 3. So now we're going to look at our behaviors. So as x is approaching our asymptotes, we're going to look at our function, and we're going to look at what our function is going to be approaching. So looking at as x approaches -3 from your negative side and your positive side, and as x approaches 2 from your negative side and your positive side, and then again look at as x is approaching negative infinity and positive infinity. So now we can take a value on the left hand side of -3, so say take the value of -3.1, and we're going to get that our numerator is positive over a negative times a negative, therefore giving us that our function is going to be positive, and therefore it will be approaching positive infinity. Now if x is approaching -3 from the positive side, we're going to have a positive all over a positive times a negative, which therefore our function would be a negative, and therefore approaching negative infinity. As x approaches 2 from the negative side, we're going to have a positive over a positive times a positive, oh sorry, no, a positive times a negative there. Pardon me. So that would give us a negative, so that would be negative infinity. As x approaches 2 from the positive side, this is where we'll have our positive times our positive, giving us a positive, and therefore approaching positive infinity. And as x approaches negative infinity, take a value again of 100. That's just my go-to value, and we get 30,004 divided by 9,894, which is actually going to be greater than 3, and therefore it will be above your horizontal asymptote. As x approaches positive infinity, we will again have 30,004 all over 10,094, which is actually going to be less than 3, so therefore we know it's below our horizontal asymptote. Next, we just want to look at, well, where's my y-intercept? So remember, my y-intercept exists when x is equal to 0, so f of 0 is going to be equal to negative 2/3. Now, what about an x-intercept? Remember, x-intercept exists as y is equal to 0, so it's actually just going to be 0 equals 3x squared plus 4. I can rearrange now negative 4 over 3 equal to x squared. If I took the square root of both sides, this does not exist. It's an imaginary number. Therefore, we have no x-intercept. So therefore, it will never cross our x-axis. So now we can use all this information to go ahead and sketch our graph. So again, our first step is to graph our vertical and our horizontal asymptotes. So our first vertical asymptote is at negative 3. So make sure to label x equals negative 3. And our other vertical asymptote exists at x equals 2. So x equals 2. And our horizontal asymptote exists at y equals 3. So now we can go ahead and actually graph this. So looking at this, you see when you're approaching, x is approaching negative 3 from our left hand side, that our whole function is approaching positive infinity. And as x approaches negative infinity, we know it's going to be above our asymptote. So we have our graph to look like this to begin. Next, we are looking between our values, our values of negative 3 and 2, so between our asymptotes. So we know that our y-intercept is going to exist between them. We know our y-intercept exists at negative 2/3. So we know we're going to have a value around here. We know also that this is never going to cross our x-axis. So as x approaches negative 3 from our right side and as x approaches 2 from the negative side, our whole function is going to be approaching negative infinity. So we can draw that in there. Looks like a parabola. And then looking at as x approaches 2 from our right hand side, we see that it's approaching positive infinity. However, when x is approaching positive infinity, we see that our whole function is actually going to be below our horizontal asymptote. So therefore, we know it's going to cross our our horizontal asymptote. Now, if we want to find the exact value where it crossed, we would set our whole function equal to 3, since 3 is our horizontal asymptote. And when you do set it equal to 3, you're going to get that your x is equal to 7.33. So you'll get your value somewhere around here that it's actually going to be crossing. So you'll get it to be crossing, and then it's going to hug your horizontal asymptote really close but from below. And then we can actually go ahead and label our function here. So we have f at x equals our 3x squared plus 4 all over our x squared plus x minus 6. Now, our last example, we wanted to determine an equation that has a vertical asymptote at x equals -1 and x equals 2 and has a horizontal asymptote in 3 different cases. Our first case is at y equals 3. So let's first deal with the fact of our vertical asymptotes. So our vertical asymptotes we know come from our denominator. So since it's at x equals -1 and x equals 2, I can just sub those values in. So it would be x plus 1 and x minus 2. So if I were to expand this, it would be x squared minus x minus 2. Now if we have our horizontal asymptote to be y equals 3, we know this comes from one of our third case actually, where our degree of the highest numerator is equal to the degree of the highest in the denominator. So therefore we know our degree is going to be x squared. So what you do is you divide those values of the coefficients. So therefore we know that this coefficient in our numerator has to be 3, because 3 divided by 1 would give you 3. So similar to b here, if we have y being equal to 0 as our horizontal asymptote, we know the degree of our numerator must be less than the degree of our denominator. We already know what our denominator is, which is x squared minus x minus 2, and I'm just going to choose x as my numerator. And see here, when we don't have any horizontal asymptotes, so we have our vertical asymptotes, however, still. Okay, so x squared minus x minus 2. And when we have no horizontal asymptote, this exists when the degree of our numerator is greater than the degree of the denominator. So I'm just going to choose x cubed. And that's our lesson for today.